This video is part of a series in which I describe how to implement a microcontroller core in Verilog. In earlier videos, I described the instruction set architecture and I went over the Verilog design in great detail. This video comes at the end of the series, but in case this happens to be our first contact, here is the EveCore project website. In this video, I'm going to discuss what you might do next. Basically, I'm saying now it's your turn to get to work. So I'll discuss various project ideas ranging from the simple and easy projects to some more complex and thought-provoking tasks that you might want to take on. Okay, so let me start by putting on my professor's hat and assigning a little homework for you to do to get you started. The first step is to get the EveCore running, and the second one is to write some assembly code programs of your own. So in order to get the EveCore running, you need to have an FPGA board. Maybe you want to buy the Go board that I used in my videos, or maybe you have something of your own already. Then you'll need to download the appropriate software for your FPGA. It would be the Lattice semiconductor software in the case of the Go board. And then run the Echo example program that I walked through in the videos. The second task would be for you to write your own assembly code program and to assemble it and then to download it to the FPGA and execute it. And so I have three simple program suggestions. The first one will be to read in a single character, either 1, 2, or 3, and then have the program print the corresponding message based on whatever character the user entered. The second suggestion is to take the multiply function that I went over in one of my videos and modify it to handle signed values in addition to unsigned values. And my third suggestion is to write a function that does binary division. And for this, you'll need to think a little bit harder about the algorithm that you're going to use. And so this will give you quite a bit of assembly language programming experience. In addition to writing a few assembly programs, you might also want to get into the Verilog code and modify the core. This will test your understanding of the core, as well as give you some experience and the confidence you need to design and build stuff of your own. I think the easiest place to start would be to add a compare and immediate instruction. So this would compare the value in the accumulator with an immediate 8-bit value, and the assembly code would look like this. Another thing you might want to do is to modify the loadm and storeM instructions. Currently, the loadm instruction takes the value in M and adds an immediate 16-bit value to compute the address, and the idea is you would modify this instruction to also allow you to use the XY register. You might also want to add a rotate instruction, or instructions in the case of left and right. And another thing you might want to do is add a multiply instruction. Perhaps you'll just do 8-bit multiplication, or perhaps you will add two instructions to do both 16-bit signed and 16-bit unsigned multiplication. This is going to be quite a bit more complicated, and you're going to have to just figure out how to do the circuitry as well as modify the assembler. And I don't know what assembly code you would use for these two instructions, but here's the way I would do it. And you might also want to add a divide and remainder instruction. And these are going to be even more difficult because you're going to have to figure out how to compute division with remainder. Another modification you might want to do to improve the usability of the EveCore is to add instructions to deal with decimal numbers, and in particular binary coded decimal. Or perhaps you want to write some assembly code functions that the user could call in order to perform decimal arithmetic. I think one particularly useful instruction would be an instruction that would convert a binary number into BCD notation. For example, the value C6 in hex would be converted to 0198, and that value is 198 in decimal. And here's the assembly code syntax that I would suggest for this instruction. Getting back to the multiply instruction, the algorithm that I discussed in a previous video involved doing a shift and add step 8 times in a row. And so the idea here is to create an instruction, which we can call mul step, that would do one iteration. That is, it would do a shift and conditional add. And so in order to make the multiply instruction more efficient, the function would just use this instruction 8 times in a row instead of having a loop and doing what it does do. Also, it might be nice to have a shift instruction that takes a variable amount. So in this case, the register B would contain the number of bits to shift and would be between 0 and 7. Or maybe you would use negative numbers to shift in the opposite direction. And that comment about negative numbers can also be applied to any rotate instruction you might want to create. So positive numbers shift, say, to the right and negative to the left, or something like that. The details are up to you. I also have a number of other ideas for EveCore projects that you might want to tackle. One idea is to write an emulator for the EveCore instruction set architecture, which would allow programmers to execute EveCore programs on their laptops. Among other things, this would allow single stepping through a program, which would make debugging perhaps a little easier in certain situations. And it would also allow for faster software development for another reason, and that is that every time you write a program and want to run it, you don't have to download it to the FPGA, but you could execute it directly on your laptop. Another idea is to modify the ALU instructions. Currently, they are 1 byte in length, so this modification would extend the instruction to 2 bytes in length. And the idea is that rather than using the A and B registers and only the A and B registers, as it is now, you would allow any arbitrary registers to be used in this format. So here I've sketched out how you might encode this operation, and you see we've got room now for the specification of 2 additional registers. I've also enlarged the function code to 5 bits, so that might give you room for, say, multiply and divide instructions or rotate instructions or whatever other operations you want to include. Another thing you might do is add more 16-bit operations. We already have the add 16 instruction that works on the X, Y, and M registers, but you might want to include a number of other ALU operations and perhaps a number of other 16-bit registers. You might want to turn A and B into a 16-bit register and C and D into a combined CD register. But at this point, it's starting to turn into a 16-bit computer, and so you might choose to give these different register names altogether. Finally, I want to wrap up with some ideas that are a bit more complex and that would require a significant amount of effort and thought. For one thing, this computer doesn't contain any support for encryption or decryption or computing secure hashes. These things are very computation intensive, and they're very important operations, I think, as time goes on, we have more malware and so on. So how would that be added to a core like this? Another problem is that this core doesn't accept interrupts. There is no interrupt mechanism. So if you want to add the ability to handle interrupts to the EveCore, you're going to have to figure out some way to enable and disable the interrupts, and maybe you'll have a bunch of different interrupt sources. So will you do this by source or just one global bit? You've also got to have some mechanism for saving registers and the condition codes efficiently. Maybe you'll end up with multiple execution levels or priority levels. You know, designing the interrupt mechanism is going to be something that requires a bit of thought and creativity. But at this point, if you do all of the additions I've suggested, you're really moving on beyond the EveCore substantially, and you're really looking at a different instruction set architecture altogether. And in fact, I have done this, and if you're interested in more complex architectures and you like my style of videos and presentation, I encourage you to look at the Blitz 64 architecture. This is a multi-core architecture that's much more involved and much more realistic and capable of handling an operating system like a Unix operating system. And so I would encourage you, if you want to move on to something a little bit more complex, to visit the website and take a look at the Blitz 64 project. Okay, that wraps up this video. Thank you very much for watching.